vision techniques, like image processing techniques. We've seen that in terms of convolution. We've seen a bit of sparse interest point detection now, and we've started to see how we can start piecing together these low-level features to reason about an image. What we're going to do now is start looking at ways that we can start further integrate this information to start making decisions about what shapes might be present in an image. And in order to do that, we need to think about things called shape descriptors and look at common ways of describing shape in images. So the first thing I'm going to introduce in this lecture is a technique called the Hopf transform, which is a way to find simple geometric shapes in an image. I'm going to talk about it in the context of finding lines in an image, but you can also use it to find more complex shapes, but not too complex because it's quite computationally expensive. We're then going to look at something called connected component analysis and how we can compute simple shape descriptors called shape factors from connected components in an image. Don't worry, I will tell you what that means, connected component. And then we're going to look at some basic shape recognition tasks and begin to talk about something called statistical moments of shape. Okay, so let's start by looking at this this image here, which is, I don't know, top of a building somewhere. You might think, looking at this image, that it's very easy to detect straight lines in this image. Perhaps the first thing you might do is run like an edge detector over that image. So the edge detection I've got here on the right is a canny edge detection of this. It's a little bit like the Sabel technique I showed you, but with a bit of post-processing. What that technique is looking for then is areas of large gradient magnitude in the image, so large intensity change. Although you might think this image would be a very easy one to extract edge detail from, when you actually look at the edge map that gets produced, you can see there are lots of little holes, even in what we perceive to be quite strong edges. And if you look at this image a little bit more closely, you can see there's a little bit of shadow that's caused the hole in the edge here, and you know, there are lots of other little holes in the edge in other places too. So, still, nevertheless, as humans, we can look at this image and pretty much figure out where the strong edges are in it from that edge map. And that's because when we look at that image, what we're doing is imposing, if you like, a mental model of shapes. We know we're looking for straight lines. We kind of look in an image for pixels that tend to be lined up in straight lines, think, oh, that's a strong edge, and I'm imposing my model of a line onto that image. There's a line there. Okay, it's this kind of top-down model fitting approach, and this leads us to talk about this thing called the Hopf transform, which is the first top-down model fitting approach we're covering on this course. As an example of one of the gaps in an edge. Okay, so before we talk about top-down model fitting, let's just think a little bit about how we might solve this from a bottom-up point of view. Imagine I did have this little bit of edge here with a hole in it. What I might do, if I wanted to start reasoning about where the big long lines are in this image is, I might say walk along the pixels, the white pixels in this edge map, and when I get to an end, I might look around to find the nearest other edge pixel and maybe jump across it and join those pixels up and carry on going. And that works very well until we start coming to more complex edges like this. And then, you know, when we come to really complex edges like this, really we haven't got a chance in being able to make sense of this. And this is because we're looking at the image in a very local way. We're trying to figure out how to join up the edges in a very focused way, where we're not taking into account the context of the whole image. And this is what motivates then this idea of doing top-down model fitting to detect shapes in images. So this top-down approach, what we're going to come to is this Hoff transform, is this process of then fitting a mathematical model of a shape to the evidence within an image. So the mathematical model of a line that we're going to use is going to be based on not y equals mx plus c, which perhaps would be your first guess at a mathematical model or equation for a line, because that equation, y equals mx plus c, can't represent all possible lines. Which lines can't it represent, for example? Which line could you not represent using your standard high school equation for a line, y equals mx plus c? Vertical line, thank you very much. That's right, because that has an infinite gradient. You need an infinite m to be able to do that. In other words, you need multiple values of y for a given x. So a function, y equals mx plus c, or more generally y equals some f of x, is not going to work to represent your line, is it? So instead, what we're going to do is represent lines in our image using an equation for an infinitely long line derived from this r and theta, where r is a vector that runs perpendicular to the line we want to model, and r is the length of it, the r is the length of that line, and theta is the angle that that line r makes with respect to one of the axes, and let's just choose x arbitrarily here. So this is the line we want to model. This dark blue line here is going to be infinitely long in this initial simple case, and we're going to describe the position and orientation of this line using two variables, r and theta, where r is this line subtended perpendicular to that line and passing through the origin, and theta is the angle of that line from the x-axis. Does that make sense? Okay, so you tell me, what range of r and theta do you think we need to be looking at in order to model all possible lines that could occur in that two-dimensional space? All possible infinitely long lines can be modelled by by variation in some range of r and theta. What would be a good guess for that range? Well, what do you think theta should range between? 0 to 2 pi or 0 to 360 degrees? Yeah, absolutely. And then what would that mean for r? R would be positive then, yeah? So we could look at all possible values of theta from 0 to 360 degrees, and then look at the positive range of r, or alternatively we could look at theta ranging from 0 to 180, and then we'd have to look at positive and negative values of r, yeah? Okay, and then, a possible upper bound on the absolute value of r might be something like, I don't know, height times height squared plus width squared, square rooted, the largest possible diagonal line perhaps in the image. Okay, so the way that we can model then that equation for that line is using this expression r equals x cos theta plus y sine theta. Okay, we can see how this would actually relate back to our equation y equals mx plus c just by substituting and rearranging this equation. So for example, if we were to say subtract x cos theta from both sides of that equation, we get y sine theta equals r minus x cos theta. And then if we divided both sides by sine theta, then we get y equals r over sine theta minus cos theta over sine theta, or equivalently or equivalently as I've written it there to be more compatible with our y equals mx plus c notation. So you can see the gradient here of this line then is given to us by cosine theta over sine theta, and the intercept of this line is r over sine theta. Okay. Hopefully you can see how that will also relate to the fact that this is a right angled triangle here. So the hypotenuse of this right angled triangle there is r, and then the adjacent in this case it's different, isn't it? So we're looking at the right angled triangle being such that the intercept is the hypotenuse and r is the opposite side, and the other side is the adjacent. Okay, so what is the value of representing a line in this way? Well, as I say, it can represent all possible lines, infinitely long lines, and therefore gives us a good way of modelling possible lines on our image. So every pair of values, what we call every tuple of values, r theta, we can consider to be a point in a two-dimensional space where one axis is theta and one axis is r. So a point in this space, this parameter space, equals a line, an infinitely long line through our image. Does everyone see that? Yeah? Okay. So what we're going to do is take that parameter space for r and theta and quantize it, in other words, break it up into some fine-grained intervals, fine-grained regular intervals. So, a sensible division of this space might be to break the range theta up into 0 to 360, so 360 different intervals, and break, given that theta is going now from 0 to the full 360, you might want to we'll look just at the positive range of r, we might want to break r up into intervals of 1, let's say, okay? And that's going to give us a quantization of this parameter space, if you like, a set of values, a set of pairs of r theta that represent all possible lines we're going to consider passing through this image. Does that make sense? So what we're going to do is treat this this search for this line as a kind of a grid search. So we're going to treat this range of r and theta as a two-dimensional array, where we within each cell, each possible value of r theta, we've broken this space up into, we're going to store a counter, and we're going to set that counter to 0 for all entries in this parameter space. Okay, so imagine you're implementing this in C or Python or MATLAB or whatever. You define a big 2D array, you set all of the elements to be 0, and every element in that array is some r theta pair. In other words, it is some infinitely long line passing through that image, or possibly passing through that image. Everyone follow? And then what we're going to do is look at our image, and having performed that edge detection, think about that black and white image I showed you at the beginning, we're trying to find the lines in. Every pixel that's white in there, that is an edge pixel, we're going to consider all the possible values of r and theta that would cause a line to pass through that value, that pixel. Yeah? So I don't know if you can see here, I'll try to do it, doesn't come out super well on this TV, is I've kind of got an image here that's black, and then you can see the little white pixels here. I don't know if you can see that. So this green dot is meant to be over the first white pixel, the first edge pixel in the image that we encounter in the image. So what I want to do is consider all possible lines that go through this this green dot here, this first edge pixel, and for every value, for every line, I've got an r theta pair, right? So what I'm going to do is for every r theta pair I identify that would generate a line going through that point, I'm going to add 1 to the respective counter in my two-dimensional array. Yeah? Does that make sense? So, for example, here's a line that passes through that edge pixel. It gives me because it's a line, I can represent it as an r theta pair. So I'm going to look up in my parameter space the counter, the 2D cell in my 2D array, so the cell in my 2D array that corresponds to that r theta pair, and initially it's going to have 0 in it, I'm going to add 1 to it, so now it's got a 1 in it. Yeah? I'm then going to find another line that passes through that point. That's going to give me another r theta pair. So I'm going to increment, that means add 1 to the cell in my parameter space that corresponds to that r theta pair. And I'm going to keep doing this for all possible lines that go through that first edge pixel I found. And that's going to add 1 to a whole bunch of cells there in my two-dimensional array. So that two-dimensional array is going to accumulate what we call votes for lines that would exist in that image. Does everyone see that? For that reason, we call that two-dimensional array, we call it an accumulator space. Sometimes we call it a Hopf space after the guy that invented this, hence it's called the Hopf transform. Okay. So then what I'm going to do is, having done that for all possible lines that go through that first edge pixel, I'm then going to do the same thing for the next edge pixel I encounter in the image, which I put a little yellow dot over. And I'm going to say, okay, let's look at all possible lines that go through that yellow dot, that second edge pixel I've encountered in the image. And that's going to cause me to increment a whole bunch of cells in my accumulator space corresponding to all the r theta pairs that pass through that yellow dot. Some of those cells might have accumulated 2 votes by now. And then we carry on doing that all the way through our image. So for every edge pixel that exists in that image. What you're probably going to realize by now is that there are certain pixels here, certain lines, that are going to get voted for a whole bunch of times. This edge pixel, when I look at all possible lines going through this edge pixel, one of them is going to be this line. When I look at this edge pixel, all the lines going through that, one of them is going to be this line. Yeah? And this line has the same r theta pair. So, whatever the cell is in this space that corresponds to that r theta pair, by the time I've gone through every edge pixel in this image, it's going to have accumulated quite a lot of votes. Whereas other cells in that space might still be at 0 or have very few votes. So having run through this process then of accumulating votes for every possible line that goes through every edge pixel identified in the image, we've accumulated votes for, or evidence for, different configurations of our model for a line. And we just simply look in the accumulator space. Having done that, we look for the maximum cell in that space, and that gives us the r theta pair corresponding to the best fit line to those edge pixels in the image. And we needn't just look for one, we might look for multiple maxima in the space. We might look for the top 10 voted cells, which give us the 10 best candidate lines in that image. Yeah.
So we apply the voting spaces around the line itself, not the pixel.
Right. So this voting space is a 2D array of counters, okay, where we split up the possible, because these are continuous values, so we split these up, we quantize these into sensible regular intervals. Let's talk later what sensible intervals might mean, okay, and we break that up into cells. Each cell has a counter in it, and then, yeah, so this space isn't about pixels, this is about r theta pairs, but to populate this space, we consider the pixels in the image. Specifically, we consider every edge pixel in the image, and for every edge pixel in the image, we consider all possible lines that pass through that edge pixel in order to increment the relevant r theta pairs in the parameter space. Does that make sense? Yeah? Then we just look for the biggest one, and that's our line. Any questions? Right, well, one question you might ask is, how do I calculate all possible lines going through one of those edge pixels? Well, actually, that's quite simple. We just use that equation for the line that I showed you a moment ago. Remember, we have our equation for a line is r equals x cos theta plus y sine theta. So what that's giving us is an expression for r in terms of theta and x and y. So given that we know our x and y, we've visited a particular edge pixel, we know its xy value, what we're going to do then is keep x and y constant and then just write a loop that loops through all the possible divisions that we've made in theta, in this case from 0 to 360 in increments of 1, as I suggested we might quantize that space in the first place. We run that loop, evaluating r for every value of theta. This then generates us, in this case, 360 r theta pairs, which are the elements that we increment in our two-dimensional array. Make sense? Yeah? So in practice, what happens is each edge pixel ends up generating almost like a sinusoid of additions to the space. You can see how we're going to get a column of this space is going to get incremented for every value of theta, right? So, and that value is r is a function of this trigonometric expression, so it ends up tracing like a sinusoid in this space. So here's a real example of a circuit board, okay, and here we've taken an example of that circuit board, we've run an edge detector on it to produce this binary mask queue of the edges, and then I've run exactly that process I just described. So for every edge pixel in this image, we figured out all the r theta pairs that generate lines passing through those edge pixels, and then we've used those values to increment the counter in this Hoff space, in this accumulator space, where this is theta and this is our r. So there's rho written there instead of r, but you get the idea. Okay? So what do you think the main advantage is then of this Hoff transform as I've described it? Deal with bad lighting. In other words, it can deal with little holes in the line. Yeah, it takes a global view, doesn't it, of the image. Can you see how it takes a global view? Because we don't start making a decision as to what the best lines are, the best fit lines are in the image, until we've processed every edge pixel. We gathered evidence for every edge pixel in the image. Yeah? So it's a global algorithm. That is the most important thing. So it's a global algorithm, makes it robust to noise and occlusion, which might cause holes to appear within those edges. What do you think the main disadvantages of the Hoff transform? Okay, so what you're suggesting there is, you say where the lines are curved, so you're saying it doesn't, you're saying if you're not dealing with straight lines it doesn't work, basically, yeah? Okay, well in the way I've described it that is true, but actually we'll see in a moment that you can do it for other shapes as well, so it's not necessarily a disadvantage. Yeah? It's slow, yeah, it is slow, yeah. So, we'll come to that in a minute, but yeah, actually one of the big disadvantages is this quantization that I glossed out, yeah?
It can also falsely detect a break when there's too close line.
Yeah, well actually it won't detect breaks, because right now what it's looking for is infinitely long lines across the image. So if there is a break, if there are two lines, actual lines...
So if there are two lines that are literally two segments that are back to back,
yeah.
Would that then register as two separate lines?
No, it would register as one line, because it's an infinitely long line at the moment, what we're looking at, yeah. Yeah. So one of the main disadvantages of the Hoff transform is this quantization level, actually, that we talked about, because we need to think a little bit carefully about how we break up our values of our theta space in order to create that two-dimensional array. If we break up the space into very coarse intervals, coarse level of quantization, then we end up getting, as you might expect, very poor accuracy of the system. Because we're only able to, let's suppose in an extreme case, we break theta up into 45-degree intervals instead of 1-degree intervals, then we're only going to be able to detect lines to the closest 45 degrees, which are probably going to be inaccurate because lines can occur at any angle in an image. If we end up dividing the range of theta, for example, to finally, maybe we think, okay, fine, I'm going to break it up into millionths of a degree then actually we get a problem as well. Because suppose that I'm looking at all my lines that pass through a particular pixel, I come up with a particular value of r and theta. Let's suppose this number line here is my number line for theta. Okay, I might say, a particular value of theta might fall into this bin, and then it might just need just a tiny little bit more value, like 1.01 or 2.01, sorry, it would just fall into this bin. Okay, so if my divisions of my theta, or indeed my r, are too fine grained, then small differences in the line will end up splitting the votes for that line across multiple bins, and they won't accumulate enough evidence to be able to detect that line robustly. So clearly we can go too coarse or too fine, and it really is just a matter of experimentation and the kind of data you're processing to figure out what an appropriate level of quantization should be. And as I said and you said, it is also a slow algorithm, because we have to do this whole populate this two-dimensional space by visiting every edge pixel in the image, and then for every edge pixel in the image we have to run this loop. Yeah, so populating this space is expensive. Okay, let's come back to that point later. So, one of the other things I talked about was how the Hopf transform models lines of infinite length, but actually we quite often would like to detect lines of finite length in an image. But actually it's quite easy to do that by looking at the infinitely long line that's been detected by one of those maxima in the accumulator space, and then figuring out how these pixels project onto the line, figuring out basically where they stop projecting onto the line and where we should terminate that infinitely long line. So let's suppose, for example, that I've taken this image here and I've detected this infinitely long line within it using this Hopf transform. What I'd like to do is figure out where I want to chop the line start and end in order to create a finite line within that image. Well, one way that we can do this is by rotating the image so that this line here is no longer a diagonal or arbitrarily oriented line, but is aligned to one of the axes. Let's suppose I want to rotate this image such that this line that I've detected in it is aligned to the vertical or y-axis of the two-dimensional space. It's easy to do that rotation because I already know what angle that line is at. It's at theta degrees, so I just have to rotate by negative theta degrees to make that whole image line up so that line is vertical. And then what I could do then is translate that line so it lies directly upon the y-axis. That again is easy to do because I know the distance of that line from the y-axis. It's just r once I've done that rotation. So I can rotate and shift and translate, in other words, that image to align my infinitely long line to the y-axis. And then I could just look at that, I could just look at the pixel coordinates along that row of the image, so along that column of the image, and figure out and just start with these edge pixels and just work inwards until I find a white pixel, and that will give me the start and end points of that line that I can then translate with an inverse translation, perform an inverse rotation, and then I've got the start and end points of that line. So I've got a finite length line. Okay, so I mentioned that it's possible to use the Hopf transform to detect other simple geometric shapes. Another popular application for it is to detect circles in an image. Okay, in fact, the Hopf transform can be used to detect any shape in an image that you can model mathematically. So in this case, we're going to use the mathematical model expression for a circle, which is going to be basically r squared equals x squared plus y squared, where r is the radius of the circle. But we're going to make it a little bit more general by just subtracting some offset a and b from the x and y before we square it, and that's going to allow us to center that circle at any point in the two-dimensional space. So our generalized equation for a circle we're working with here is r squared equals x minus a squared plus y minus b squared, where x and y are the free variables. So we can immediately see now that the location and the scale, the radius of that circle are governed by 3 parameters now instead of 2. So we can still use this idea of the Hopf transform, but our accumulator space now is 3-dimensional. So we need to build a 3-dimensional array to accumulate the votes. So it's still possible, but actually it's going to take a really long time now to populate this accumulator space, because for every pixel that we encounter that's an edge pixel in our edge map, we're now going to consider all possible circles that go through that, which basically means we're going to have to calculate an R for all possible values of A and B. So we've got a nested loop here for A and B now, instead of just one loop, which is what we had before. So it still works out that you can do this in real time on modern hardware. But you know, if we were looking at even more complex shapes, we started looking at that rectangle finding problem I talked about when I was looking at license plate detection in cars in the first lecture. That was a four-dimensional search space. Really, 4 dimensions is about as far as you want to go with this, and then it is a little bit slow. It's not real time anymore anyway. Okay, so actually it turns out, we won't go into the detail, but it turns out that a Hopf transform can be generalized in such a way that any shape, any contour can be defined as having 4 free parameters, and therefore can just about be detected with a Hopf transform using something called the generalized Hopf transform, a chap down in Southampton invented some years ago. But anyway, we're not going to go into that on this course. If you want to look at it more in that detail, that green snake book on the course, there's a lot more detail on it. Yeah, so this is my point really, that the Hopf transform becomes impractical for more complex shapes. Right, is everyone happy with the Hopf transform there, how I've described it? Yeah, any questions on that at all? So that's our first example really of a top-down model fitting approach to computer vision, where we've modeled the shape we want to find geometrically and then look for evidence in that image, collected evidence, namely to make a globally optimal decision using all pixel information as to where that model would fit. Okay. Right, I wanted to talk about something else now. We've got a fair amount of time left, so I'm going to talk now about other ways of measuring and recognizing shape. And in particular, we're going to start looking at something called a shape descriptor. So shape descriptors are ways of taking a digital fingerprint of a shape to create a point in a high-dimensional space that characterizes that shape. So just like an image descriptor was a way of taking a fingerprint of an image and transforming an image to a point in a high-dimensional space, shape descriptor is basically the same idea. We're gonna do it for the shape in an image. Okay. So we're going to start looking at some basic shape descriptors now. But before we get to that, I'm going to just talk a little bit about how we can break an image up into its components in order to then address each of those components in turn to compute those shape descriptors. So let's suppose we have a simple scenario where we're working on a system for factory, and the factory is making plates, and the plates get made and they go along this blue conveyor belts, and there's a camera above the blue conveyor belts, and it takes photos of the plate as it goes past. And what we're trying to do is figure out when a broken plate goes past, so we can, trigger some servo or something, chuck it in the bin. Okay, so in order to do that, what we're going to do is separate out the region of the plate, or broken plate, from the background, which we've engineered to be a distinctive colour, blue. So how do you think you would go about creating an image like this, what we call a binary mask, of this region of interest of the plate picked out against the blue. Yeah.
For every pixel value where the certain RGB value has a threshold greater than.
Okay, well you could do, yeah, so the suggestion is that we somehow threshold the image, so we could look at the blue channel of the image and threshold it or something like that. Yeah, I mean, think back to that sky example I gave you. It's a slightly better way of doing that, right? When we were talking about this sky classifier before, we talked about taking a patch of sample image containing just the conveyor belt and looking at the RGB values of the pixels in that patch and building an eigenmodel in the RGB feature space, such that then when we were presented with an image like this, at test time, we can measure the distance of every pixel, measure that Mahalanobis distance of every pixel to that eigenmodel, and threshold it at some level in order to decide if it's plate or conveyor belt. Yeah? So your suggestion was kind of a good one, because you were saying threshold on the RGB values, but remember, what you'd really be saying when you say threshold on the RGB values is threshold on some average RGB value for the background, which, if you remember, is assuming that spherical decision boundary in the RGB space, which is not usually the case. So we'd usually use an eigenmodel for this. By the way, if you look at the past exam papers, you'll see quite often I set questions in this kind of a style. Given a scenario, how would you extract a binary mask of an object? Given a scenario, what sort of shape descriptor would you use? These sorts of things. So, it pays to think a little bit about these sorts of questions I'm asking in the course, as to how you might go about answering them. Okay, so assume that we've done this thresholding of the Mahalanobis distance. We've converted then this RGB image into this black and white image. Remember, with the special name for that is a mask, or binary mask, containing the object of interest. Well, immediately we can see one way of solving this problem. Well, if we could somehow count up how many connected components there are in the image, if there's more than one, plate's broken. Okay, so that would be kind of a trivial way to solve this. It's not a brilliant way, because suppose some of the bits of fragment could have fallen off the conveyor belts, and there's now a broken plate, and it's not circular. So ultimately, we're going to come down to talking about a shape descriptor that measures how circular that region is. But before we get to that, I want to talk about how we can break up this binary mask into these individual white regions, what we call connected components of the image. So each of these white regions here is what we call a connected component of the image. It's basically a part of the binary mask that's connected in terms of north, south, east, west to a neighbouring white pixel. Yeah. So I've labelled here 3 of the connected components in the image to really illustrate that point. Normally, when we talk about connected components, we talk about an image that has either 4 or 8 connected. What that means is, if it's a 4 connected, if we're doing 4 connected processing, it's a 4 connected component. It means that we've considered whether a given pixel that's white has an adjacent pixel north, south, east, west, the 4 points of the compass. If it's 8 connected, we consider northeast, northwest, southeast, southwest as well. Okay, but 4 connected is usually enough to be considering when we process these images. So so what we're going to do then is figure out a way of iterating through the connected components in this image, because what we're going to do is iterate through the connected components, and for each connected component, analyze its shape. Okay, so how do we iterate through connected components in the image? In order to understand how we do that, we need to be aware of an algorithm that computer graphics people use all the time, and I'm sure you've used too in paint programs like Photoshop. Other paint programs are available, you know, when you do that little pot of paint and it fills up a region in the image. Okay, that is called a flood fill. So. Okay, so the flood fill algorithm is an example of a recursive algorithm. Who's heard that term before, recursive algorithm? Okay, a recursive algorithm or recursive function is a function that calls itself. Okay, so in this function here is all you need to implement a flood fill. What we do is we call upon the flood fill algorithm starting off at what we call a seed point. So we pick an XY position in the image we want to start the fill from. And we also pick a color that we want to fill the region we've clicked on with. So if this is our binary mask here, and we've got a region here of 255s, this is our connected components. Let's imagine that we've clicked on this bottom pixel of the connected component that was 255, and now we basically want to fill that entire region now with 128. So our X and our Y would be that start coordinates there, and that color would be 128. Okay, so this is like a grayscale image. Okay, so our flood fill algorithm is going to basically get the color of that pixel we've just clicked on, which was 255, so that's old color. And it's going to set the colour to the new desired colour, which was 128. Okay, which is like a mid-grey value, if you like. 0 being black, 255 being white. And then we're then going to look north, south, east and west, and we're going to look to see if that pixel has that old colour, that 255 in it. And if it does, then we're just going to recursively call the flood fill algorithm at that position to perform the fill from that point. And so on. And then once we've called the flood fill, let's suppose we've got to this first line here. Actually, no, it would be this one here from the north, wouldn't it? Y minus 1. We're looking here to see if this pixel here is equal to the old colour, equal to 255. Yes, it is. And it's not the colour we want to fill, which is 128. No, it's not. So we're going to call upon the flood fill algorithm again, seeding it at this particular point. Yeah? It's important to check that it's not the colour we want, otherwise the thing will never terminate and just keep calling itself the whole time. So you can see how that recursive call would then call on this pixel, that would then call on this pixel, this would then call on this would then call on this, and so on recursively until the entire image is filled. Yeah?
Doesn't matter where the seed pixel is.
No, it's deterministic, so you could have clicked on any of those pixels and it would end up filling the whole region. So this is just a mechanism really to replace a connected component's colour with another colour in an image. So we're going to see why that's important. Oh, there we go. Animation. I'm going to see why that's important in a minute. So what we're going to do is use this flood fill algorithm to iteratively select components. Let's imagine we start with our connected components here, our binary mask of our connected components. What we're going to do is iterate through the pixels and find the first white pixel we encounter and flood fill from that point. Okay, let's pick a colour that's not in use, so not black or not white. Let's pick mid-grey, but I'll just use green here because it's easier to see. Okay, that will then cause this whole region to be shaded grey. Yeah, 1 to 8. Okay. We can then look at that image, having performed that fill, and pull out all the pixels that are of value 128 to create an image that just contains that region. Yeah? It's a way of extracting just that region, because we kind of highlighted it. A simple way to do that would to be visit every pixel in turn, say, does that pixel have color 128 or not? Yes or no? Create a new binary mask containing just that mask. Then we go do some processing on that shape. We might analyze how circular it is, for example. And we'll come to that in a minute. Once we've done processing that region, what we're going to do is then call upon that seed point again, but flood fill it to be black. And that will effectively erase that entire connected component from the image. We're then going to carry on iterating through our image to find the next white pixel. But it won't be any of these because we just deleted them from the image. It'll be this one. Then we flood fill that grey. Process it. Flood fill it black. And continue until we get to our next pixel, which honestly would probably be that one. I don't know why it's shaded green there, but you get the idea. Probably because I iterated through the image this way, actually, but anyway. Does that make sense? So, the algorithm then, in summary, is, let's assume we got an image, which is this binary mask of our connected components. Our mission is to iterate through each connected component and do some processing on it in some way. We're going to loop through all the pixels, X, Y, and that mask, and we're going to look to see if we're on a white pixel. When we've encountered a white pixel, we're going to call on our flood fill algorithm to fill that image, that connected component grey. And then we're going to create a mask called working mask by just isolating those grey pixels and do some analysis on it. When we're done with that analysis, we're going to flood fill at that same point using black. Go around our loop again to find the next white pixel, in other words, the start of the next connected component. That make sense? Any questions on that? Yeah, so that's just sort of re-illustrating the point, really. Find the connected component, the first white pixel, shade it grey, process the grey bit, shade it black to delete it, come to the next pixel. Don't expect you to read that. That's just in your slide deck is a more kind of formal description of the algorithm there. It's basically what I've just been saying. So, okay, so what we've shown there is a way of isolating our plate or broken plate fragments from the conveyor belt and visiting each of those connected components in turn to do some analysis. What sort of analysis do we want to do? Well, we're going to compute some simple shape descriptors from that connected component. We're going to start on our lecture tour of shape descriptors by talking about the simplest kind of shape descriptor called shape factor. Okay, shape factors are just simple ratios that we can calculate that describe useful properties of our region. So, for example, if we were wanting to achieve this plate. Is the plate broken or not classification exercise, a really useful measure we could look at would be compactness. Compactness is the ratio of area over perimeter squared. normalized such that it's in the range 0 to 1. Okay. What do you think the most compact shape would be? That is the shape that has the biggest area for a given perimeter. Not a square. Circle. Yeah? What do you think the least compact shape would be? Well, it could be anything, couldn't it? It could be some strange, squiggly, highly concave shape. There's a really long perimeter and not an awful lot of area. Yeah? So, this compactness then is actually a measure of circularity. So what I could do is visit each of my connected components in my image and measure the compactness of each one. And if any of those pieces that I visit have a low compactness score below a threshold, then I could consider that to be a fragment of broken plate because it's not circular. So that would be a great way of solving this problem. Much better than counting the number of connected components, because as I say, some of them might have fallen off the conveyor belts or something like that. Some other really useful shape factors for other tasks are things like the aspect ratio. The aspect ratio describes the ratio of the width to height of a bounding box that fits around the connected components. We talk about bounding boxes quite a lot in computer vision. A bounding box is the smallest rectangle that contains a region. So I've drawn the bounding box for this region here in red, for example. The convexity of a shape can be measured by the ratio of its area to the area of something called its convex hull. A convex hull is the minimum size polygon that can fit around, sorry, the minimum convex polygon that can fit around the shape. In the 80s, a lot of people spent an awful lot of time figuring out how to make the best convex hull algorithm. MATLAB has an algorithm called Quick Hull implemented in it that does this very, very fast. But so that you could compute the convex hull of this shape and then measure the area over the area of the convex hull. By the way, the area of the shape is very easy to calculate. How do you calculate the area of a connected component in pixels? Count the pixels. Count the white pixels. Yeah. How would you measure the perimeter of the shape? Yeah, could do that. Yeah, that's a good suggestion. You could get a little window and move a window over this, and you could look within the window, and if the window has got black and white in it, it's an edge pixel. So yeah, and count how many of those you encounter. You could run an edge detection algorithm over it using a convolution, and then look at how many pixels of white coming out of that as well. Yeah. Okay. And there are other ones like waviness, technical term, perimeter of the convex hull over the perimeter of the shape. Another trick is to calculate something called the Euler number, which is basically the number of holes that are in the shape. So if you were doing character recognition, for example, capital B is the only letter in Roman letter that has two holes, and so on. How do you think we could create a shape? These are all called shape factors. There's another shape factor called the orientation, which would be the angle of the principal axis of this shape. How do you think we could compute that? using the techniques covered on this course. Eigenmodel, yeah, absolutely. If I looked at all of these white points here as points in a two-dimensional space, that's a point distribution. I can build an eigenmodel from it, and I'm going to get its centroid, and I'm going to get its principal eigenvector as well as its second eigenvector. And the angle that principal eigenvector makes to the vertical would be theta, would be this orientation of the shape. Well, then it would pretty much be undefined. Yeah, in the sense that it could be anything.
So then would we be able to use that as a rough
No, it wouldn't be a good choice then for circles. No. We might be able to measure the length and width of this shape by looking at its the ratio of its eigenvalues, for example, of that eigenmodel. So that would be an alternative to the aspect ratio that's sensitive to the orientation of the shape rather than the bounding box, which is rectilinear. So, yeah. So yeah, we could use an eigenmodel for that. Yeah, as I said. So, let's recap then. How would we solve this broken plate finding task using shape factors? What's step one? You've got an image of a plate there. Is it broken or not? What's the first thing you do? Yeah, binarize it. So create a binary mask. Yeah, how do you do that? Eigenmodel. Yeah, measure the Mahalanobis distance of each pixel to an eigenmodel made of the color from the color distribution of the conveyor belt and threshold that Mahalanobis distance. And then what do we do with that binary mask? What's the next step? Break it up into its connected components, yeah? Using that flood fill algorithm we just talked about. And then for each connected component, what do we do? Measure its compactness, right? To see how circular it is. And if that compactness is less than the threshold, then we would say, yeah, the plate's broken. Okay. As I say, quite important you really think about these problem-solving questions. That is the style of the exam. Okay. Well, let's use the last few minutes then to just introduce a final concept for today, which is going to build up into another way of describing shapes, another kind of shape descriptor. And this is to consider what we call statistical moments or of a shape. So let's suppose that we have this set of pixels here. Let's imagine it's just one row of pixels in an image. Okay, we can calculate some useful properties of this image. We could look at the coordinates of the pixels, and we could look at the values of the pixels. If I were to think about that as like a number line where the coordinates of the pixels are 1, 2, 3, 4, 5, then we have coordinates for the pixels in the range 1 to 5, and we have some function of those coordinates, f of x, which is our image, that gives us the values 0, 1, 1, 1, 0 for the pixel values. And we have 5 of those pixels, so we're going to have n equals 5. So the mean, or centroid of that image, I mean, clearly it's going to be 3, right? Yeah? We call that mu. You would normally perhaps consider calculating the mean in a simpler way than this, but in fact this is a more general way of writing down the mean. What we're saying is we're going to sum up the product of each coordinate with the value of that pixel. We're going to form that summation and then divide by the sum of the values. Okay? Can everyone see how that is equivalent to just calculating the mean average of those pixel values? Yeah? Okay? So that is a way of expressing mu, the mean or centroid of that data. It's perhaps an overcomplicated way of doing it, but as we'll see, that way of expressing the mean is something called a statistical moment. Specifically, it's what we call a statistical moment about 0. And the mean is an example of or is in fact the first moment computed about 0. And we have a special shorthand for that. We call it m subscript 1. In general, the equation for the alphth moment, yeah, so m alpha, is the sum of the coordinate raised to the power alpha multiplied by the content of the image or a signal in this case, divided by the sum of those values. So you can see where alpha was 1 when we were calculating the first moment, but that was equivalent to our equation there for the mean. Everyone follow that? Just looks like an overcomplication at the moment, and for convention we just say m0 is 1. Okay, actually moments about 0 aren't particularly useful. What we usually are interested in computer vision is moments computed about the mean, what we call central moments. The equation for a central moment is exactly the same, except instead of having this x to the power alpha, we have x minus mu, where we've pre-computed mu, the mean of that distribution. So it's using a mean subtracted version of x in that equation. That's a much more useful equation because it allows us to express in that single equation a lot of useful statistical properties. For example, if we were to set alpha to be 2, then that equation would be equivalent to the equation for the variance of that distribution. Okay? So we're just, to be clear, we're using this shorthand now. Instead of m and a subscript for the moment about 0, we're using alpha and a subscript, mu and a subscript to indicate the alphth moment about the central moment, the moment about the mean. Can you see the equivalence between that equation and the equation we perhaps are more used to using for the variance of a point distribution in 1D? So the third central moment is equivalent to something we call the skew of the data. So if the mean is the centroid of the data, and the variance is how much our data spreads about the mean, the skew is like how lopsided the data is, how much of it is on one side of the mean versus the other. Yeah? And mu4 is kurtosis and so on. There's a whole bunch of these useful statistics that we can compute. So I'm going to leave it there for today. But next time we're going to talk a lot more about how we compute the statistical moments in 2D because that is a way of expressing a shape descriptor of these connected components. So in summary, in this hour, we've looked first of all at the Hopf transform to find simple shapes in images, specifically lines and circles. We then looked at what we mean by connected components in an image, and we described the flood fill algorithm as a mechanism for isolating and iterating through the connected components in an image. We then looked at some really basic shape descriptors, what we call shape factors, which are really just simple ratios we can compute about properties of a shape. But later we'll see much more sophisticated and useful shape descriptors. Hopefully you've seen the start of how you can start applying these computer vision techniques to simple tasks like shape recognition. And we started talking about statistical moments, about zero and the mean, but only in one dimension for now. And there's that snake book I mentioned if you want to read a lot more about Hopf transforms, Martin Nixon's book. Okay, thank you very much.